Welcome to Homework Lib.
We're going to have the following situation of different charges that are essentially on only two dimensions because the y-coordinate for all of them is going to be equal to 0. And we know that one of them is going to be located at the minus a. Let me draw this properly just to have the coordinates like somewhat correct. So we're going to have minus a, minus a, and a on the x and y axis. So what we're going to get is that we're going to have a charge q at a comma minus a, so over here. Let's call this q1. Actually, this would be q2. Q1 would be at minus a on x, a on y. This would be q1. Next up, on the final one would be at minus a and minus a, the one over here, q3. And with this, we want to know what would be the resulting electric field at this point at the a, 0 point. So first of all, notice that Q1 is only going to contribute to the x direction of the axis, and Q2 is only going to contribute on the y direction of the axis. This is because the distances that we have here are going to be directed on those axes there. And we are also going to know that the distance over here the distance in which that we're going to have is going to be equal to the square root of 2a squared plus 2a squared, which is 8 times a squared. So the distance would be 2 times the square root of 2 times a. Okay. For the other two, the distance corresponds directly to 2 times a. 2a and 2a over here. So with this, the electric field on x is going to be equal to the electric field due to Q1 plus the electric field from the x contribution of Q3. We know as well that the angle that we're going to have here, theta, and theta over here, and theta, all of them are going to be the same, and they're going to be equal to 45 degrees. And since sine of 45 degrees and are going to be the same, so let's just remember that sine of 45 degrees equal to cosine of 45 degrees, and this is going to be equal to 1 over a square root of 2, because we're going to take this value as reference. So in this case, the electric field due to Q1 is going to be equal to K Q1 divided by the distance squared, which is 2 times a squared, so 4a squared, plus the electric field due to Q3 on the x direction. In this case, we can apply, using this theta as reference, the cosine of 45 degrees. As I mentioned, it doesn't matter because sine and cosine in this case are going to be the same. So this is going to be equal to k times Q3 divided by the distance squared. So this is the square root of 8 times a squared. So 8 times. So the factor over here would be 8 times a squared times the cosine of 45 degrees. As I mentioned, the cosine of 45 degrees is equal to the square root of 2. And we also know that Q1 is going to be equal to Q3, and this is also going to be equal to Q2. So in this case, the electric field on the x direction would be kq divided by a squared multiplied by the factor 1 over 4 plus 1 over square root of 2 times 8. And this is going to be on the positive I direction. Now for the electric field on y, what we're going to have is something very similar. Actually, it's going to be exactly the same thing because this is going to be electric field due to Q2 plus electric field of Q3 on the y direction. All of this, of course, on the j. And this is going to be k times Q2 divided by 4 times a squared plus k times Q3 divided by a times a cubed, a squared. times the sine of 45 degrees. But as we mentioned, sine of 45 degrees and cosine of 45 degrees is the same. And as you can see, all of the charges were to be exactly the same. All of them are going to be equal to Q. So the electric field on Y is going to be KQ divided by A squared times 1/4 plus 1 over the square root of 2 times 8 on the J axis. So we can express the electric field as KQ divided by A squared, that is going to multiply 1/4 plus 1 over square root of 2 times 8 on I plus the same value on J. Or if you want to use the numbers, the electric field would be KQ divided by A squared and 0.338 if you want on I plus 0.3384 on J. And never forget the units Newton per coulomb. So now on the second case, which would be part B, we're asked what happens if Q at minus A, minus A, 0 is equal to minus 2 times Q. So what is going to happen is that each of the factors are going to change, but regardless, because of the symmetry of the problem, the components of X and Y are going to stay the same. So now the component on X, in this case, would be the first factor stays the same, KQ squared divided by A squared. But now the second factor is going to change by a factor of minus 2. So this is going to be minus 2 times KQ divided by 8 times A squared multiplied by the cosine of 45 degrees. So 2 and 8 cancel out. We're going to do it up with 1/4. And this becomes electric field on X is going to be equal to KQ divided by 4 times A squared. And we're going to factorize it as 1 minus 1 over square root of 2. And this would be on the I direction. The result on Y would be exactly the same. KQ divided by 4 times A squared, 1 minus 1 over square root of 2 times on the Y axis. So the electric field on the second case would be KQ divided by 4 times A squared times, if you want to put it, 1 minus 1 over square root of 2 on I plus 1 minus 1 over square root of 2 on J. Which, if you're going to put it as a number, would be KQ over 4 times A squared times 0.29289 I plus 0.29289 in J. So those are both of the possible results that we have. Normally I prefer the one on the top. It's more aesthetic and better to track down and to see what is happening. The same thing happens over here with the original case. So with that, it would be all. Thank you very much and have a good one.